So hi everyone, welcome to our tutorial, Recent Advances in Pre-trained Language Models. Why do they work and how to use them? And I'm Cheng-Han Jiang, and my name in Mandarin is Jiang Cheng-Han, and I'm a first-year PhD student at National Taiwan University. And I'm very happy to share with you some recent advances in pre-trained language models in today's tutorial. So first, I would like to introduce the other two instructors. The first one is Yongsong Zhang, and he's a second-year PhD student at MIT CSAIL. And the other tutorial instructor is Professor Hongyi Li, and he is an associate professor at National Taiwan University, and he's also my PhD advisor. So in this tutorial, we will introduce some advances made in pre-trained language models in 2021 and 2022. And through our tutorial, we hope that the audience who are not familiar with pre-trained language models, or those who want to know how to use pre-trained language models in their domain of interest, can have a better understanding of how those pre-trained language models can be used. And for those audience who are familiar with pre-trained language models, we believe that this tutorial can serve as a good review of what the whole research community have achieved in recent years. And we hope this can help inspire new ideas and to push the community forward. So overall, we hope after this tutorial, the audience can have a better idea of what these pre-trained language models, or why these pre-trained language models are so powerful, and how can we apply these models in different scenarios. So in the first part of our tutorial, Professor Li will first give a gentle introduction to what pre-trained language models are. And in the second part, Professor Li will illustrate some interesting findings from recent years that try to understand why these pre-trained language models are so powerful. And after having a basic idea of what pre-trained language models are and the potential reasons for their exceptional performance, we move to the main part of our tutorial, which is how to use those pre-trained language models. So in part 3, Yongsong will introduce a method called contrastive learning that has become more and more powerful and more popular in natural language processing in recent years. And Yongsong will show how this contrastive learning is used with pre-trained language models and what improvement has contrastive learning made in natural language processing. And after part 3, we will take a 10 minutes break. And after the break, in part 4 and part 5 of the tutorial, I will introduce some new fine-tuning methods that have been showing up in recent years. And these fine-tuning methods are proposed to solve some problems when we want to deploy these pre-trained language models in real-life use cases. So in part 4, I will first introduce a spatial fine-tuning method called parameter efficient fine-tuning. And in part 5, I will go through how to use pre-trained language models when we have different amounts of data. And the tutorial will end with some short summaries, and we will discuss some future research directions. So now I'm going to hand it over to Professor Li to start with the introduction part.
Okay, thanks Cheng-Han for the opening. Then I'm going to share my screen. Okay, can you see my screen? Okay, so let's start the part 1. So part 1 is a very brief introduction about pre-trained language model. And I believe most of the audience are already familiar with pre-trained language model. So this part will be very brief just to make sure everyone is on the same page. So I believe all of you are familiar with deep learning for human language processing. So today, if you want to build a summarizer, which take a document as input and output a summary, if you want to use deep learning to solve the task, you need to collect some paired data. You need documents and their summaries to train a deep model. Then you train a sequence-to-sequence model, then you can do summarization. Or if you want to do machine translation, translate Chinese into English, then you also need to collect some paired data. you need to collect some Chinese sentence and its corresponding English sentence with a large amount of paired data, then you can train a machine translator. And to use deep learning to solve the problem of human language processing, for each task, usually you need to collect a large amount of training data. For machine translation, millions of data, billions of data, billions of paired data are usually necessary to achieve high quality machine translation system. However, there are lots of different tasks for human language processing. Here, I just list a few of them. Besides that, for each task, there are lots of languages. There are around 7,000 languages in the world. So it is almost impossible to collect paired data for all the languages and for all the tasks. So there needs to be a different way to solve the problem. So here comes the framework of pre-training. The basic idea of pre-training is like this. First, you pre-train a model from unlabeled data. So with unlabeled data, you pre-train a model which develops general purpose knowledge. I know sometimes in the literature, to pre-train a model, sometimes you can use labeled data. But here in this tutorial for pre-training, we means use unlabeled data to develop general purpose knowledge. And I have to emphasize that during the pre-training, the model we obtain is task agnostic. It is not targeted at a specific task. And this pre-trained model have different names today in the literature. So besides call it pre-trained model, it has more fancy name. Some people call it self-supervised model, and it has an even more fancy name, foundation model. So as you know, lots of people are crazy about foundation model recently, and this is the pre-trained language model. This is the pre-trained model. Then after we have a pre-trained model, we will use it in some specific task. And there are many different ways to use a pre-trained model. So in this tutorial, you will hear all different kinds of manner to pre-train the model. Here, I only talk about the most common way, that is fine-tune the pre-trained model. So during the fine-tuning, you have labeled data for each task, and with labeled data for each task, you can fine-tune the parameter in the pre-trained model so your model can solve different tasks. So here I'm going to introduce the most common pre-trained model in natural language processing, the most well-known one, which is BERT. I believe all of you know this model. So how is BERT pre-trained? The idea is simple. It's pre-trained by a method called masked language model, MLN. So when you pre-train the BERT model, first you sample the sentence from your database, and you mask some of the terms, some of the words in the sentence. Then the learning target of BERT is to recover the masked word. So the BERT will try to recover the word which is masked here. So this is the basic idea. Okay, so there are many different ways to pre-train a model. Here, this tutorial is not a complete survey. Here, I just list some of the survey paper for your reference. Then after you have the BERT model, how to use them in the downstream task. Let's say you want to do sentiment analysis. So you collect some training data, you have some document, and you label the document as positive or negative. Then you can use those label data to fine-tune the BERT model. Then you can do sentiment analysis. On the other hand, if you want to do question answering, you collect some label data, you have context, query, and the answer to the query. Then you use the label data to fine-tune the model. Then you can do question answering. And this slide is to give you a specific example how to fine-tune the model. Here, I will going to use sentiment analysis as our example. In the following tutorial, you will see all kinds of methods to leverage the self-supervised model. Fine-tuning is just one of the many possible examples. Okay, so this is your pre-trained model. This is BERT, and you take a sentence as input, and you put a CLS token in front of the sentence, and the model will output a representation, and you add a linear model on top of the pre-trained model, and the linear model will output the classification result. And the linear model plus the pre-trained model is the whole model you are going to solve a specific task. The linear model has to be trained from scratch, but the pre-trained model is, the model here, the pre-trained model is already pre-trained. We will use the pre-trained parameter, the parameter obtained from pre-trained as the initialization of the model here. So you do not have to train the model. You do not have to obtain the parameters from scratch. Okay, so as you know, BERT achieved very good performance in lots of benchmark corpus. And one of the most well-known example is the amazing performance of BERT on the GLUE benchmark corpus. GLUE is a general language understanding evaluation. Today, when you want to evaluate how good a pre-trained model is, usually you will not only test your model, you will not only fine-tune your model on just one or two tasks. You will fine-tune your model on a wide range of different tasks. And in the GLUE benchmark, there are 9 different tasks. And if you have a self-supervised model, if you have a pre-trained model, usually today people will evaluate your model on all the different tasks to show that your model really learns something general and it can be used in a wide range of different tasks. And this is the performance of the self-supervised model of the pre-trained language model on GLUE benchmark. And here, each column represents a model, and different points represent the performance of a specific model on a specific task. And here, the black line is human performance, and the blue dotted line is the average performance of a self-supervised model of a pre-trained model on all the GLUE tasks. And in this figure, you can find that in the end, with good enough pre-trained model, machine can even outperform humans' performance on this benchmark corpus. So this is an evidence to show that pre-trained model is very powerful. And I believe probably some of you already aware of many other great achievements of the self-supervised model on a lot of NLP benchmark corpus. So this is for natural language processing. The same technology can be used in other domains. For example, almost the same idea can be applied on speech. So besides BERT, you can also have speech version of BERT. So it is very easy to collect a large amount of unlabeled data from the internet. And with those unlabeled data, you can use the same idea as BERT to pre-train a model. So you have a speech version of BERT. And in the speech community, there are already lots of well-known, widely used pre-trained models. I just list some of them here. And after you have the pre-trained model, it's pre-trained from speech, you can also fine-tune the model for different speech processing tasks. For example, you can use the model for speech recognition. You collect some utterance, and you have text label for the utterance. Then you can fine-tune your speech version of BERT. Then the model can do speech recognition. And you can also use the same pre-trained model for speaker recognition. You collect some utterance, and you label the speaker identity of those utterance. And so you have some label data for speaker recognition, and you use those label data to fine-tune the speech version of BERT. Then you can make the model do speaker recognition. And those pre-trained speech model, they can also be used on a wide range of different tasks. Just as I have mentioned, BERT achieved good performance on all the GLUE benchmark tasks. And just like BERT, speech version of BERT, speech pre-trained model can use on a wide range of different speech-related tasks. And in the speech community, there's also a benchmark corpus to evaluate whether those pre-trained models are general or not. This benchmark corpus is called Speech Processing Universal Performance Benchmark, or SUPERB. In SUPERB, it includes a wide range of different speech processing tasks, cover many different aspects. Here for different aspects, I use different color. And does those speech pretrained model achieve good performance on those tasks in the super benchmark? Here I put the reference for the super benchmark. You can check the paper here, or if you want to listen to the video, I also have an English version of introduction of the result on the super benchmark. So you can visit the link here. And this is, of course, this is not a complete survey. There are many different ways to pre-train a speech, to have a speech pre-trained model. Recently, I have an overview paper with many excellent researchers. I also put the link of the survey paper here. So if you want to have a complete understanding of self-supervised speech pre-trained model, you can read our survey paper. Okay, so this is part one. Let's move to part two. Why pre-trained language model works. I think one of the most common reason why pre-trained language model work is they are contextualized word representation. I believe all of you know word representation like word-to-vec or globe, and BERT can be considered as an advanced version of word representation. It's contextualized word representation. If you analyze the representation in BERT, you can find that it not only encodes the token to the representation, and the token with similar meaning have similar embedding. This can already be done by globe or word-to-vec. It also considers the contextualized information. It also considers the context of each word. So the same word can have different representation. If you use the BERT representation to represent the words, the same word can have different representation based on the word sense. And here, this is just a toy example, but in the literature, you can easily find some real example. For example, here in the paper, visualizing and measuring the geometry of BERT, the author show the representation of lie. As you know, lie have many different meaning. It can refer to untruth, it can refer to lie down, or it can have geographical meaning or mathematical sense. And the BERT know that the same word with different word sense will have different representation. So this is already a common sense in NLP community. And people also want to know what BERT has been learned from the pre-training. What does each layer learn in those pre-trained language model? Because there are lots of paper working in this direction. We can call this series of paper as a new discipline called BERTology. And one of the very common way to understand what each layer is learned is probing those layers. Probing means given the representation from a specific layer, then you learn a classifier for the information you want to know. For example, if you want to know whether the representation contains POS information, then you train a POS classifier. The POS classifier takes the representation as input and predict the POS text of the input words. Or if you want to know whether those representations contain the information of NaN entity, then you learn an NER, NaN entity recognition classifier. And the NER classifier takes the representation as input and try to predict the NaN entity of the input words. And intuitively, if the classifier gets higher accuracy, that means the representation contains the information you are looking for. If the POS classifier can have high accuracy based on the representation, then you know those representations contain POS information. Or if those representations obtain very good performance on NaN entity recognition, you know the NaN entity information are included in the representation. This is just the most intuitive idea. However, if you go through the literature, you will find that higher classifier accuracy does not always refer to encoding more information. We do not really have time to explain the reason, but I just want to mention that when you use the technique of probing, you need to be very careful. And here I list some reference. So if you want to use the probing technology to analyze your pre-trained language model, make sure you have go through this paper. You know how to interpret the probing results correctly. Okay, so let's see what people find based on probing. A very common finding, lots of paper already talking about that, is bird rediscover the typical NLP pipeline. So given a sentence, the bird will first analyze most surface form, do some very basic analysis of the input words. Then it do some basic syntactic analysis. Then it do some more high-level semantic analysis. So the first few layers include surface information, and the middle layer do syntactic parsing, and the last few layers do semantic understanding. And there are several evidence, several papers talking about that. So in the paper, A Structural Probe for Finding Syntactic in Word Representation, the author tried to transform the representation into a parsing tree. So they invent some way to probe whether the representation includes syntactic information. And they use a very simple model to transform the representation into the parsing tree. And they evaluate the accuracy of the parsing tree. The result is shown at here. The horizontal axis is different layer, and they have two models. One is bird-based with 12 layer and bird large with 24 layer. The vertical axis is the accuracy of the parsing tree. They have two evaluation measure. The larger, the better. And it is clear that the middle layer of the pre-trained model get highest accuracy. Means those middle layer include the most syntactic information. And this is another analysis from the literature. So this is from the paper, What Does Bird Learn About the Structure of Language? And the author tests many different tests, including some tests only need to understand the surface form, some tests need to understand syntactic, and some tests need to do semantic parsing. And you can find that if you do the probing, if you probe different layer, you can find that the first few layers are good at this kind of surface related task, and the middle layer are good at syntactic parsing, and the middle to the top layer are good at semantic analysis. However, you can also easily observe that there's a little bit messy here. So the semantic information spread from the middle layer to the top layer. It has a very large overlap with the syntactic parsing. This is another example. I'm not going to go through the detail here. So this paper is very well known. Bird rediscovered the classical NLP pipeline. So I put the reference here so you can go through the paper yourself. In all, the paper also tells you that the first few layers for easier tasks like syntactic analysis, and the last few there for more high-level semantic understanding. However, recently some paper show that this kind of understanding oversimplify what pre-trained model learn. So it is very hard to find what is done by each layer. It is difficult to identify that a specific layer is for syntactic parsing and another specific layer is for semantic parsing. A more accurate understanding of the pre-trained model is they do syntactic analysis and semantic analysis in this way. So there's no specific boundary for different kind of text. They are all mixed together. People agree that Usually the first few layers tend to do something simpler and the last few layers tend to do more high-level semantic understanding, but there is no clear boundary between syntactic parsing and service form and syntactic parsing and semantic understanding. You can read those papers for more detail. And actually how the input sentence is processed is very sophisticated. So this kind of figure oversimplify what pre-trained model is really doing. What pre-trained model is learned from the unlabeled data. And the mechanism can be very sophisticated, and actually it is input dependent. And besides birdology, there's another series of work we call bird embryology. So bird embryology tries to analyzing what bird learn during the training process. And here I list two papers starting bird embryology. One is from my research group. So this is the paper of Cheng-Han. We call it language model embryology. And this is the paper from Noah Smith. And based on its title, it's very easy to understand what they are working on. They call it probing across time. So in this series of paper, we want to know when the bird knows POS tagging, syntactic parsing, or semantic understanding during the training process. I put the reference here for your consideration. And people also want to know how many data is needed to pre-train a model. So this is also similar to bird embryology, but a little bit different. They want to need how many data is needed, how many training sentences are needed to make the bird understanding syntactic, semantic, or even word common sense. These figures are from the paper, When Do You Need Billions of Words of Pre-trained Data? So let's just talk about the left figure. So here the horizontal axis is different amount of training data, and the vertical axis is the performance. And the green line is the result of syntactic learning curve, and the pink line is the learning curve of semantic parsing, and the light blue line is the result for Winogrand, so related to word common sense. So you can find that you only need relatively little data to learn syntactic, but you know much more data to make the pre-trained model have common sense about the word. And there's also some theoretical analysis. So here, there is a concept called intrinsic dimension. Due to time limitation, I cannot go through the detail, but just keep in mind that smaller intrinsic dimension means better generalization of a model. And in this figure, so this figure is from intrinsic dimensionality, explain the effectiveness of language model fine-tuning. Here, the horizontal axis is the training process, is the number of updates, and the vertical axis is intrinsic dimension. Smaller intrinsic dimension means better generalization. And you can find that if you analyze the pre-trained model on different downstream tasks, here are several NLP downstream tasks, and you can find that in those downstream tasks with more and more pre-training, the intrinsic dimension becomes smaller. That means the model have better generalization capability if you pre-train them more on the training data. So this is some theoretical analysis. So until now, we show that bird learns something from the text. It learns some linguistic stuff. And there is also some theoretical evidence. However, here, I'm going to share some experimental results that will change your that will change your understanding of the pre-trained language model. Here, we are going to show that those pre-trained language models are not only good at natural language processing tasks, they have cross-discipline capability. So if you have a model pre-trained on human language, you can apply them on very different on the task not related to natural language processing at all. Here, in our paper is Bird a cross-discipline knowledge learner. In this paper, we are going to show that the pre-trained language model can be used in DNA classification or protein classification. So this paper is also from my group. This work is mainly done by my previous student, Wei Cong. Okay, so here we are going to use BERT in downstream tests like DNA classification. So let me introduce DNA classification a little bit. In this downstream task, you have some DNA sequence. And as you know, in DNA sequence, there are four types of symbols, A, T, C, and G. Each DNA sequence is a sequence composed of A, T, C, G, four types of symbols. And for each sequence, we have a label, we have a class. This is a simple classification task. For example, row sequence are EI, and row sequence are labeled as IE, and row sequence are labeled as N. I don't really know the meaning of the label here. For me, it's just the typical classification task. And this is how we use BERT to train on human language on the DNA sequence. DNA sequence have four symbols. Then we replace each symbol with an English word. For example, we replace A with we, T as you, C as he, G as she. So given a DNA sequence, AGAC, it becomes an English sentence. We, she, we, he. Of course, this sentence is just nonsense. It's meaningless. Then we use BERT to train on English. We use BERT to take this sentence as input, and this BERT will output a representation for a linear classifier, and the ultimate goal is to do DNA classification. And here, just like how people usually use the BERT model, the BERT is pre-trained on English and fine-tuned on DNA classification. And I have to emphasize that here the BERT is pre-trained on English. I know lots of people already try pre-train a model on DNA sequence and use it in DNA classification. And of course, this framework shows good performance. But this is not the case here. What we want to do here is the model is pre-trained on human language, then fine-tuned on DNA classification. We want to see whether pre-trained on something very different can be helpful for DNA classification or not. And this is the experimental result. We tried 3 different protein classification tasks, 4 DNA classification tasks, and 1 music classification task. The result in the red box here is the result without initialization. And the result here is the result with initialization. We initialize the model by pre-train on English. And it is clear that on all the different tasks, pre-training on English is helpful. Pre-training on English is helpful for protein classification and DNA classification. So what do we learn from here? This shows that those pre-trained language models learn something more than linguistic information. Those pre-trained models learn some general skill. This general skill can apply on other classification tasks not related to human language. And I also want to convince you that this is not a coincidence. We tried many different models, include original bird, Roberta L bird, bird C means Chinese bird. We tried different kind of pre-trained model. And here is the result of DNA classification, protein classification, and music classification. The blue bars means we use a pre-trained model, but pre-trained on human language. And the orange bar means train from scratch without pre-training. And you can find that it is clear that pre-trained on human language is always helpful for DNA classification, protein classification, and music classification. And we also want to know why those models become better with pre-training. And as you know, a machine learning technology can be helpful for 2 different aspects. One is it improves the optimization. The other is it improves the generalization. We want to know a pre-trained model is helpful for which aspect. So let's first take a look at the optimization. We analyze the learning curve on all the different tasks. Here, I only show one example, but all the other tasks look similar. So the orange curve is trained from scratch. And the blue curve means we use pre-training, pre-train on English for a specific DNA or protein classification task. And here you can find that with pre-training, your loss can be lower than train from scratch. This shows that pre-training make the optimization easier. Then for generalization, we try to pre-train, not pre-train, sorry. We try to fine-tune the pre-train model and the train from scratch model on the training data until they get very low training loss. So these two curves are for training loss. We train the model with sufficient iteration until their training loss are very close to zero. So two different models achieve the same training loss, achieve the same performance on the training set. Then we analyze the accuracy on the development set. Because this is accuracy, so the higher the better. And it is clear that even though on the training set, pre-train and scratch get the same performance, for development set, pre-train get better performance than train from scratch. This shows that pre-training improve the generalization capability of the model. So pre-training improve not only optimization, but also generalization. So pre-training is helpful for both optimization and generalization. And we are not alone. Other group, so this is the group from Bayer from Berkeley, and they also have very similar finding. They also find that a model pre-trained on human language can be used on other tasks. They even use the model pre-trained on human language on image classification. And they also show that even though model is pre-trained on human language, they have some reasonable performance on image classification. And they have a very fancy name in their title. They call this kind of pre-trained model universal computation engines. So we already show that cross-discipline is possible for those pre-trained language model. So you can pre-train on human language, apply on some very different tasks. Then we think in a reverse way. So here, this the experiment below is from the paper done by Cheng-Han and me. We published the result at AACL this year. So if our downstream tasks are NLP tasks, can we pre-train the model without using human language? This is possible because we already know those pre-trained model has cross-discipline capability. So we use some artificial data to pre-train the model. We use some rules to generate sequence of tokens. Then we use those artificially generated token sequence to pre-train the language model. Why we want to do that? Because by generating different kinds of sequence, we can make our pre-trained model have different capability. And we want to know what is the key factor for the success of pre-training. So if we have pre-trained model with different capability, we can know which kind of capability is most important for the success of pre-training. So this is the pipeline. So we have some token sequence generated by some rules. So this is artificial sequence. They are not real human language. And we do mask LN, mask some tokens. The model is learned to recover the mask tokens. Then in our downstream task, we are going to use those models to train on artificial token sequence. We are going to use those models on NLP downstream tasks like sentiment analysis. So the model have to take an human language, have to take a sentence, English sentence as input, and output the POS tag, not the POS tag here, output the sentiment classification result of the sentence. And because this model is trained from token sequence, but the input in the downstream task should be English. So we have an ID, we have a mapping table to transform the ID into text. And this table is random generated. Okay, so we map an English sentence into a token sequence. Then you add a CLS token in front of the token sequence, and the model output representation, a linear classifier determine its sentiment analysis result. And we will fine-tune the model as how people typically use the self-supervised model. And I have to emphasize again, in our pre-training, the model have never seen human language. The model are pre-trained on artificial generated token sequence, but our downstream tasks are NLP tasks. And here is some result. So here the vertical axis is the absolute improvement compared with training from scratch. So here we show the average performance on the group task, and we show the absolute improvement here compared with training from scratch. So the result, the value here is the larger, the better. And this blue bar is the result for English. We train on English, so you can consider this as the upper bound. And here, this very small red bar is the result with random generated token sequence. And we found that if your artificial data, if your pre-trained data is completely random generated without any pattern, without any rules, is completely random generated, then the pre-trained do not provide any benefit. This experiment is also very meaningful. It showed us data plays the role, because I have wondered, probably pre-trained itself is why pre-trained is successful. Probably the data do not play the role, so cross-discipline is possible. But the experiment results showed us data plays the role. Data is still important for the success of pre-training. Then let's take a look of another result. Here, our generated sequence have paired token. So we use a very simple rule to generate the token sequence. In this sequence, the token have pair. The tokens are paired. So if you have 7 here, you can find another 7 in the sequence. If you have 3, you can find another 3 in the sequence, and so on. And we can find that even though the rule for generating this sequence is very trivial, the performance is actually amazing. We get around 15% absolute improvement with this kind of artificial data. This is the result of using real human language. Using English, we only get 20% improvement. But with this kind of paired data, we already get 15% improvement on the group benchmark. The reason here is probably because the structure in the data is critical. Probably if your data have some structure, pre-trained model can learn something from the structure. And we found that Dan Jarevsky already have a paper with some similar finding. This paper is not conducted on a self-supervised model today, not conducted on BERT, but they also show that pre-train your model on structural data is helpful. However, is the structure explain everything? Here, I'm going to show you another experiment. Here we use another rule to generate the sequence. So this is the rule, very, very simple. Given a sequence with consecutive IDs, in this example from 1 to 64, we random shuffle the token sequence. Then we mask some tokens here, and the model train on this kind of artificial generated sequence. And this kind of sequence do not really have an structure, or at least you cannot say it do not have an explicit structure. However, even though we train the self-supervised model, even though we train the pre-trained model on this kind of sequence, we just random shuffle the consecutive token sequence. We can get pretty good performance. The result is at here, almost as good as paired data. We get around 12% absolute improvement. Why this happened? One possible explanation is to predict the mask token in this sequence. Your pre-trained language model needs to go through the whole sequence. Probably the capability of go through the whole sequence is one of the key factors for the success of a pre-trained model. Here I have another evidence. The evidence here is we generate different length of consecutive tokens. For example, here 4 means we only generate 4 consecutive tokens, and we also random shuffle them. And here the results show that if the consecutive tokens become longer and longer, the pre-train become better and better. So if you have longer consecutive tokens, the pre-train will become more powerful. This shows that learning to read a long range in a sequence is crucial. If the model can learn to read a longer sequence, if the model can learn to read a longer range in an input sequence, then it becomes more powerful in the downstream NLP tasks. So this is one conclusion from our paper. Are there other factors that also influence the results? Are there other key factors for the success of pre-trained model? We don't know. This is an open question for you to have more investigation. And there are more related paper. Another paper, their title is Masked Language Modeling and the Distributional Hypothesis. All the word matters pre-training for little. They show that even though you random shuffle your input sequence, when you pre-train your model, you train your model on this kind of unsyntactic sentences. And they found that here they try many different models. We cannot go through the detail here. Just keep in mind that the model at this region means the model trained on the sequence with very little older information. And you can find that compared with the result here and the result here, they do not make much difference. The only difference comes from COLA. And as you know, COLA, the pink line here, is a syntactic analysis test. So it looks like if you pre-train your model with unsyntactic data, they cannot learn syntactic information, but they still achieve good performance on other tasks. And here is another recent paper. They also pre-train their model by artificial language as what we did in AAAI this year. And they also have very similar conclusion. They found that pre-trained model on artificial data can achieve good performance on NLP downstream tasks. Okay, so this is the conclusion remark of part 2. Due to time limitation, we cannot go through the concluding remarks. Just back to our title of part 2, why do pre-trained language model works? The short answer, I hope you do not feel too disappointed, is I don't know the answer yet. This is an open question. Today, we just go through some research direction to know what people are thinking, what the researchers are thinking. Okay, so this is for part 2. Then I'm going to hand over to Yong-Song for part 3.
Hi everyone, I'm Yong-Song, a second-year PhD student from MIT CSL. Today I'm going to talk about some recent advances in contrastive learning for pre-trained language models. Contrastive learning has been widely applied in self-supervised learning for many domains, including computer vision and speech processing. The model pre-trained using contrastive learning has achieved state-of-the-art results in these domains. However, in NLP, contrastive learning is a recently emerging direction. So we will first start with why we need contrastive learning for NLP and why it is more difficult to apply contrastive learning for NLP tasks. So let's first talk about why we need contrastive learning and how to do contrastive learning. So we need contrastive learning because we want to obtain a good representation space such that similar inputs can have similar representations in the embedding space. For example, if you have 2 images from dogs, their representations should be similar in the vector space. And if you have 2 different augmentations from the same image, they are referring to the same object, so their representation should also be similar. So this kind of similar data pairs, we call them positive pairs. And on the other hand, if you have two images that from two different objects or from two different classes, their representation should be dissimilar from each other. And this kind of data pair, we call them negative pairs. So how can we train a model to maintain this kind of property in the embedding space? We have a lot of different contrastive learning framework can achieve this kind of effect. And there is a very, very famous framework called Sinclair. And the idea is very simple. It just do two different augmentations from the same image, and then the training objective will make these two representations from these two augmentations be close to each other as much as possible. And for any other random sampled negative pairs, they just make the representation be dissimilar to each other. And this kind of contrastive learning framework has been achieved successful results on the computer vision downstream tasks. However, in NLP, contrastive learning is not very popular as we have here in computer vision. And one possible reason is that actually people has been using some ideas similar to contrastive learning for NLP, but we don't call them contrastive learning. For example, if you look at the training objective of BERT, the masked language modeling task, you can see we have a sentence here, how's the weather today? And we mask one token in the sentence and replace it with a mask token. And in the output layer of BERT, we try to predict which token has been replaced, what's the original token. So here, our input instance will be the contextualized representation of mask token. And we want to match this representation to the non-contextualized representation of the correct answer weather. So we can see these two representations as kind of positive pairs. And for negative pairs, because for our prediction test, we need to make the representation, the contextual representation of mask to be dissimilar to all the non-contextual representation of all the other words in the vocabulary. So actually, we also have negative pairs. So basically, training the NLM model is kind of similar to training a contrastive learning task. But there's a difference because we have finite vocabulary size for BERT. It's around 30,000 of vocabularies. So this finite vocabulary set prevents us to do any negative sampling process. We can use all the possible examples, all the possible words in the vocabulary as your negative pair. So we can just train MLN as a simple token level classification task without using negative sampling. However, there is also some other task that has infinite possible inputs. For example, if you are dealing with sentence level task, we have infinite combination of words. So we have infinite possible sentences in the world. So it's not possible to use all the sentences in the world to train your model. So we need the negative sampling process. So the sentence level task will be a good field to apply contrastive learning to learn a good representation space. So in the following of this tutorial, I will mainly talk about the sentence level representation. So I will first introduce why we need sentence level representation and what's the model before BERT came out and what's the model after BERT came out for sentence level representations. And most of this model after BERT is about doing contrastive learning based on BERT. So for the sentence level representation, why we need this kind of model? it's because we want to use this kind of sentence encoder as a backbone that can be used for a lot of different downstream NLP tasks. And the benefit of using this kind of sentence encoder is that we can fix this sentence encoder and only use it as a feature extractor. So we don't need to fine-tune this model for any downstream tasks. And we only need to train a linear layer and to do a simple classification, and we can achieve good performance even without a lot of label data. And also, if we have a sentence encoder model, we can extract the sentence embedding for all the sentences in the corpus, so that we can do clustering or semantic search very easily just by inner product, because we can measure the similarity of all the possible sentence pair very easily. And also, if you have an unsupervised method that can train a sentence encoder, that will be very desirable, because we can apply to all the languages, not only in English. So we can train a good sentence encoder even without any parallel data. So in the following of this tutorial, I will mainly focus on supervised method instead of supervised methods. So let's go back to the time that BERT haven't came out. So before BERT came out, there's already some papers working on sentence embeddings. So for example, in the skip solve vectors in 2016, they tried to train a sequence-to-sequence model and to encode the previous sentence and then try to decode the next sentence. So the vector between the encoder and decoder can be seen as kind of sentence embedding for the previous sentence. So that we can use that vector as a good sentence embedding. So after this paper, there is another paper called Quick Solve Vectors in 2018. They also doing some kind of next sentence prediction, but the difference is that they don't need the decoder. They can just use a classifier to try to classify which sentence is the correct next sentence. So these two models, even without the help of BERT, they can somehow achieve a good performance for sentence embeddings. But in 2018, BERT came out and it changed the whole NLP community, and all the people started using BERT as their backbone for any NLP downstream task, including sentence embeddings. So people start to try whether we can just directly obtain sentence level representation directly from BERT. And unfortunately, people found that if you just take the average of the BERT embeddings, or you take the BERT CLS vectors, you will obtain a very bad result. It's even worse than doing average growth embeddings. So why is that happening? So it's because there's one problem in BERT's embedding space. It's called anisotropic problem. So it means that the representation space has some kind of degeneration, because all the embeddings in BERT representation space occupy a narrow cone in the vector space. So it largely limits the expressiveness of the vector space. So some papers start to try whether we can fix the BERT embedding by doing some transformation to the embedding space. So in this paper, BERT Flow, they try to do an invertible mapping from a BERT embedding space to a standard Gaussian latent space. So by doing so, they can improve the performance on the STS task. STS task here is a sentence textual similarity task. It's basically constructing by a lot of different sentence pairs, and we have human ratings for all these sentence pairs. And the metric we use here is the Spearman correlation between the model predicted scores and the human ratings. So you can see after applying BERT flow, we can obtain a much better result compared to simply do average for BERT embeddings. So there is also another paper called BERT whitening. They do a more simple way to fix the BERT embeddings. So they use a simple whitening post-processing method, and their performance can be slightly better than BERT flow. Okay, so after these two post-processing papers, people start to think about whether we can further fine-tune the BERT model and to extract the better sentence embeddings from BERT. So in the following, I will talk about a lot of different contrastive learning methods to extract good sentence embeddings from BERT. So if we want to train contrastive learning model for a natural language sentence, we have a problem here. We don't know how to do the augmentations for natural language sentence. For computer vision, we can just simply do random cropping, random flip, or grayscale to obtain high quality augmentations. But because of the discrete nature of natural language, it's not easy to do this kind of operations for a sentence. So in the following papers, they try to design some augmentations or some methods to construct the positive pairs. The first paper here is called Decouter. In this paper, they try to produce the positive pairs by random sample spans from the same documents. And the spans here need to be overlapping or adjacent to each other. And they also have different strategies to sample negative pairs. For example, they sample hard negatives from the same document, and they sample easy negatives from different documents. And by doing so, they can achieve a much better result compared to BERT flow or BERT whitening. So it's a huge performance improvement using this contrastive learning method. And at the same time, there is another paper called Concert. In this paper, they try all the possible augmentations in the token embedding space. For example, they try adversarial attack, they try token shuffling, cutoffs, and dropout on the token embedding space. And they found that this method can also improve the performance of the STS task. And the performance is similar to the Decouter paper. And they also try to see which augmentation method works the best. So here you can see the shuffle and token cutoff are better augmentation compared to feature cutoff and dropout. And besides designing these positive pairs, we can also just try to generate the positive pairs from another language model. So in this paper, Dino, they try to generate the positive pairs by GPT-2XL. So they just have as input sentence and they try to generate two different continuation from GPT-2 and use these two different continuation to train your contrastive learning model. So here you can see the result of Dino is even better than Decouter and Concert and also better than BERT flow. So it shows that it's possible to somehow generate positive pairs by another language model. And another method is about the bootstrapping method. So I think some of you may have heard of the BIOL paper. So BIOL tried to do contrastive learning without negative examples. So actually it's not contrastive learning. They just have positive examples. And they try to train this model by matching the representation from an online network to a target network. And the target network is actually the moving average of online network. So this can prevent the representation space from collapsing. And a paper also tried BIOL for sentence embedding. So here you can see the result is better than BERT flow and some other post-processing methods. However, it still falls behind the contrastive-based methods like Decouter, Concert, and Dino. So these results show that maybe contrastive learning with negative pairs is still a better way to learn representation for sentences. So the next paper is a very famous one. It's called CMCSE. And in this paper, they show that you can just simply do some dropout mask as your augmentation, and you can get a state-of-the-art performance. And the dropout mask augmentation here is not the same as the one that we used in Concert, because in Concert they are doing some masking in the when embedding vectors. But here the dropout mask is all the dropout layers in the transformer layers. So what they actually do is they have the same input sentence and they forward this sentence to the transformer twice. And because the transformer will sample different dropout mask for different forwards, so you don't actually need to modify the model architecture. You can just do 2 different forwards and you can get a good augmentation. And their result is even better than Decoder, Concert, and Dino. The performance has a big improvement. And actually, the author have tried all the other augmentation methods like random cropping, word deletion, word replacement, NLN replacement, but none of them is better than doing nothing, but just changing the dropout mask inside the transformer layer. So this experiment showed that changing dropout mask is a simple but super effective way to do the augmentations. And they also try different training tasks, like we do next sentence prediction in quicksort, and we can also try this for BERT, but it's not as effective as self-prediction. And they also try a dual encoder and compare it to a shared encoder. So the results show that one single encoder is a better sentence encoder. So here they also have some ablation study about the dropout mask. So they try to apply the same dropout for 2 positive inputs. By doing that, you will obtain exactly the same representation for the positive pair. By doing so, the performance will drop significantly because your model is not going to learn anything by matching 2 already the same inputs. And they also try different dropout ratio here, and they found that the best dropout rate is around 0.1. In the CMCSE paper, they not only do the unsupervised setting, they also do a supervised setting. And the positive pairs are produced by the NLI, the Natural Language Inference dataset. So in this dataset, we have an entailment sentence and a contradiction sentence. So they use the entailment sentence as a positive pair and the contradiction sentence as the hard negative pair. So by doing that, they can get even better results compared to the unsupervised CMCSE. And the experiment also showed that if you use some other different supervised data to produce the positive pair, like doing back translation as a paraphrase, this kind of method is not as effective as using entailment data as positive pair and the contradiction data as negative pair. And so if you compare unsupervised CMCSE with supervised CMCSE, you can see there's still a big gap between these 2 models. So it shows that there's still a large room for unsupervised models to improve. And the author of the CMCSE paper, they also try to evaluate the embedding space and see why CMCSE performs much better than other models. So here they use alignment and uniformity to measure the quality of the embedding space. Alignment means how close the 2 representations from the positive pairs are aligned together. And the uniformity means how well the representations are distributed in this vector space uniformly. So they try to plot the uniformity and alignment in this 2D plot. And the y-axis is alignment and the x-axis is uniformity. So you can see if you directly take the embeddings and take the average of the BERT embeddings, you get a very good alignment. But your uniformity will be very bad because of the anisotropic problem of BERT. And if you do some post-processing for BERT embeddings, you can get a much better uniformity because now your representation space is a Gaussian distribution. But your alignment will be compromised. So that's still not a very good representation space. So you can see SYNCSE here, it not only achieved a good uniformity, but it also achieved a good alignment. So that may be a reason why SYNCSE can outperform all the other methods. After SYNCSE, people start to try to extend SYNCSE to multilingual settings. So here, the paper MSynCSE, they have a very surprising finding. They found that if you use a multilingual model like multilingual BERT or XLMR and fine-tune them with the SYNCSE objective with only English data, the model can align all the languages together, even without using any parallel data for other languages. So we can see in the figure here, the representation space for XLMR is not aligned at all. So all the languages are separated. But if you fine-tune this model with SYNCSE objective, all the languages are aligned together. And this is without the supervision from parallel data. And here's the result for cross-lingual retrieval for the MSynCSE model. So we can see the performance of MSynCSE that are trained with only English NLI datasets. It's very close to the performance of a LabC model. The LabC model is a multilingual sentence encoder released by Google. This model is trained with a lot of translation pairs, so it's fully supervised. So the result here achieved by the MSynCSE model is very surprising to me. Yeah, and I expect that there should be some different ways to improve this kind of unsupervised multilingual sentence encoder model. So after SYNCSE was published, we learned that the augmentation for natural language is very hard because word deletion, synonym replacement, sentence cropping, and back translation, they are all outperformed by a simple dropout-based augmentation. So another question is, how can we utilize these augmentations even their quality are not so good? So here let's take a step back to think about why we need these augmentations. It's because we want to make the representations invariant to these kinds of augmentations. However, because the quality of this augmentation is not so good, so making the representations invariant to this augmentation will actually hurt the downstream performance. So does that mean these augmentations are not useful at all? I think no, because we can try to use these augmentations in a completely different way. We can try to make the representations be aware of, but not necessarily invariant to the augmentations. So let's look at some examples in computer vision to understand this idea. In computer vision, we have so many different augmentation methods like grayscale, 4-4 rotations, vertical flips. And you can see grayscale is a very good augmentation method. It can achieve much better result compared to a baseline if you use grayscale to produce the positive pairs. However, 4-4 rotation is a really bad augmentation method because you can only obtain a much worse result compared to the baseline. So here we can try to do the things differently. We can try to, instead of using this augmentation as positive pairs, we can try to make the model be sensitive to these augmentations. So by doing so, you can see the performance of training a model to be sensitive to grayscale will be worse than the baseline. And if you train a model to be sensitive to 4-4 rotation, the performance is actually better than baseline. So here the results show that all the augmentation methods should be useful in some ways, but you need to choose the right way to utilize them. For grayscale, you should make the model insensitive to it. And for 4-4 rotation, you should make the model be sensitive to it. So how can we have these two properties in a single model? So we can have a multitask model here. So on the left-hand side is a regular Sinclair model that tries to make the representation invariant to the grayscale augmentation. And on the right-hand side is a prediction task. We try to predict the rotation angle of an input image so we can make the model be sensitive to 4-4 rotation augmentation. So how can we apply this concept to learn sentence embeddings? So here we propose a model called diffCSE. It's also a multitask model. And on the left-hand side, we have a regular SimCSE architecture that makes the representation be insensitive to dropout mask augmentation. And on the right-hand side, we have a generator and discriminator. The generator will replace some tokens in a sentence to produce augmentations. And the discriminator will try to predict whether one token has been replaced by the generator or not. And the model on the right-hand side is very similar to Electron model. It's also a generator and discriminator. But a huge difference here is that the discriminator is conditioning on the sentence embedding produced by the sentence encoder. And the gradient of the discriminator can be backpropagated into the sentence encoder. So the sentence encoder will try to compress the original information as much as possible to help the discriminator to distinguish the difference between the original input and the modified input. So here, our model is actually doing a kind of diff operation between two very similar inputs. So that's the reason why we call our model diffCSE. After training this model, we discard all the generator and discriminator and only use the sentence encoder for inference. So the result of diffCSE show that it's much better than SimCSE by 2% on the STS task. And also you can see what's the difference between SimCSE and diffCSE by looking at the retrieval results. So here we have a query sentence. This is not a problem. And the top one retrieval result from SimCSE will be, this is a big problem. So these two sentences has the opposite meaning, but their structure is very similar. So the SimCSE model was misled by the sentence structure. However, for diffCSE, the top one choice will be, I don't see why this could be a problem. So this sentence has a similar meaning to the query sentence, but their structure are very different. So this result shows that diffCSE will not be biased by the sentence structures, while the SimCSE are more easy to be biased by the sentence structure. Okay, so the next paper I'm gonna introduce is about using pumping to further improve the performance of SimCSE. So in this paper, PromptBirds, they try to design or search good prompt templates to better extract the sentence embeddings from BERT model even without fine-tuning. So previously in SimCSE paper, they still use the CLS vectors to extract sentence embeddings. But in this paper, they try to use some templates like this sentence of X means mask. And the X is the sentence of your input. And you use the final layer representation of the mask token as your sentence embedding. So by doing so, you can actually get a much better result, even you don't fine-tune the BERT model. And so to further boost the results, you can fine-tune this model with contrastive loss. And the way that they produce the positive pair is very special. They use two different templates to generate the sentence embedding from the same sentence. So these two sentence vectors can be used as a positive pair. And by doing so, their result is actually much better than SynCSE and also better than DeepCSE. And it's almost the current state of the art. And after PromBERT, there is another paper further improved the performance of PromBERT by injecting ranking-based information. So in this paper, Rank Encoder, they try to refine the embedding space of existing models like SynCSE or PromBERT by injecting the ranking information from the whole corpus. So if you have a corpus with 5 sentences, you can compute the sentence embedding by SynCSE, so you have 5 data points here. And if you have a new input to the model, you can compute the cosine similarity between this input to all the other examples in the corpus. So you can obtain a ranking vector here. And if you have another input, you can also do the same thing to extract another ranking vector. However, you can observe that these two inputs are not very distant from each other, but their ranking vector are completely different. It's because you need to consider the interaction between the input sentence and all the other sentences in the corpus. So even though these two sentences are not very different, their ranking information may be very different. So this kind of ranking vectors actually increase the resolution of the embedding space if a specific region has a lot of data examples in the corpus. So it's kind of renormalizing the embedding space. And after we obtain this ranking vector, we can normalize the ranking vector and get a real sentence embedding to do the downstream task. And also we can further train a new encoder to match the cosine similarity of the ranking vectors to further boost the performance. Here the result of rank encoder is even better than PromBERT and all the other models we introduced previously. And this kind of framework can be compatible with all sentence encoders, so it's a very powerful technique. And here we can further investigate why rank encoder can achieve better performance by looking at the embedding space of this model. So you can see the embedding space of PromBERT. There are so many regions that has a lot of examples clustered together. However, because the rank encoder can be aware of the fine-grained interaction between the similar sentences, so it can smooth out these clusters. So the embedding space of rank encoder will be more uniform. And you can see the uniformity of rank encoder is much better than all the other models after applying this, injecting this ranking information. Okay, so that's all the content I want to show you today. And the conclusion I have here is that at the beginning, SynCSE told us the gap between unsupervised model and the supervised model is still very large. But after a lot of papers continue working on this direction to improve SynCSE model, the performance of an unsupervised rank encoder now is comparable with a supervised SynCSE or a supervised PromBERT. So it's very surprising that at the end, the gap between unsupervised model and supervised model can be reduced by a lot. And I expect that contrastive learning techniques can help us to better extract a representation from the existing pre-trained language models. That's all the content I want to share with you today, and thanks for listening, and I'm very happy to take any questions.
So, welcome back to our tutorial. And in the previous part, Yong-Song and Professor Lee has introduced the basic ideas of pre-trained language models, and Yong-Song has introduced how to use contrastive learning with pre-trained language models to to provide better sentence representations, and that can be used in different downstream tasks. And in the following part of the tutorial, I'm going to share some interesting fine-tuning methods that can be applied in different downstream tasks. So let's start with part 4. Back to our tutorial. In this part, I'm going to introduce a special type of method for fine-tuning pre-trained language models called parameter-efficient fine-tuning. Let us start this part by recalling the standard fine-tuning introduced at the tutorial's beginning. Given the pre-trained language model, such as BERT, and 4 different downstream tasks, 1, 2, 3, and 4, we wish to fine-tune on the 4 different tasks using the standard fine-tuning. In the end, we will have one model for each downstream task, and each model will have roughly the same size as the pre-trained model. This is problematic since the size of the model is very large, and it requires a lot of space to store all those different models for different downstream tasks. In order to solve this issue, parameter-efficient fine-tuning is proposed. The core idea of parameter-efficient fine-tuning is that each downstream task will only have a very little amount of task-specific parameters. So, given a pre-trained language model and task 1, the downstream model's parameter for task 1 consists of 2 parts. The first part of the parameters is exactly the same parameter of the pre-trained model, and the other part is the task-specific parameters for task 1. The task-specific parameters are far less than the parameter size of the whole pre-trained language model. Likewise, for task 2, the parameters are composed of the original parameters of BERT and the task-specific parameters of task 2. This is the same for task 3 and for task 4. Now, all 4 tasks share the same BERT parameters, and each task has its own task-specific parameters. This can greatly reduce the number of parameters we need to store. If we want to deploy these fine-tuned models on the same device, the parameters we need to store are roughly 1 BERT model instead of 4. Before explaining how exactly parameter-efficient fine-tuning reduces the task-specific parameters of the downstream tasks, I'm going to revisit the standard fine-tuning that fine-tunes the whole model. This will give a better idea of parameter-efficient fine-tuning methods. So back to standard fine-tuning. What is standard fine-tuning doing? In short, fine-tuning changes the hidden representations extracted by the transformer models. Before fine-tuning, given an input sentence, the transformer model calculates the hidden representations of each token in the input sentence. The hidden representations, denoted by H, are just any features extracted by the transformer model. It can be the output of a transformer layer, and it can also be the output of the self-attention layer. After fine-tuning, the model's parameters are updated, and the updated parameters will generate a different set of hidden representations, denoted by H'. Given the same sentence, the hidden representation is different for the pre-trained model and the fine-tuned model. So we can consider the fine-tuning process as a process of changing the hidden representations of the pre-trained language model, such that those representations can be better used for the downstream task. If our goal is to change the pre-trained hidden representation H into H', then we might not need to fine-tune all the parameters in the model, but only fine-tune a very small fraction of the parameters. This is what parameter-efficient fine-tuning tries to do. The first parameter-efficient fine-tuning method I'm going to introduce is the well-known adapter. By adding a special submodule called adapter and training these adapters during fine-tuning, we can change the hidden representation of the model after fine-tuning. Adapters are small trainable modules that are inserted in transformers. A transformer layer is composed of two parts, the multi-head attention layer and the feed-forward layers. Adapters are inserted right after the multi-head attention layer and the feed-forward layer. When fine-tuning the pre-trained model on a downstream task, only the parameters in the adapter are updated. The rest of the parameters in the pre-trained transformers are frozen and not updated. In this part, the modules in pink are the modules not trained during fine-tuning, while the yellow ones will be trained during fine-tuning. So what is in the adapter module? The adapter has two feed-forward projection layers connected with one nonlinear activation. There is also another skip connection that bypasses the feed-forward layers. Assume that the adapter shown on the right represents the adapter after the multi-head attention layer. Then the input to the adapter layer is the hidden representation H calculated by the multi-head attention layer. H takes two different ways in the adapter layer. One is the skip connection, so H will not be changed in this path. The other way is the one with feed-forward layers. The first feed-forward layer first projects H into a low-dimension space. This space has a dimension less than H. After the nonlinear activation function, the feed-forward up projection layer projects its input back to the dimension of H. Last, the result of the two different ways are summed together to obtain the final output of the adapter module. The skip connection doesn't change the input H of the adapter, and we can view the feed-forward path as creating an incremental change, delta H, based on the original H. When adding the incremental change delta H obtained from the feed-forward layer and the original H from the previous layer, the adapter modifies the hidden representation that is calculated by the pre-trained language model. In this way, the hidden representation calculated by the pre-trained model is changed by the adapter. When using adapters for fine-tuning, we only need to insert adapters into each transformer layer and adding a classifier head on top of the pre-trained language model, and fine-tune the whole model on downstream task. The only parameters that are updated are the parameters of the adapter and the classifier head. The rest parameters in the pre-trained models are fixed. So after fine-tuning, all the downstream tasks fine-tuned from the same pre-trained model have the same set of parameters of the pre-trained language model, since those parameters are frozen during fine-tuning. Each task will have its task-specific parameters, which are the parameters of the adapters and the classifier head. By using adapters, the task-specific parameters for each task are significantly reduced. Next, we turn to another kind of method called LoRa. Similar to the adapters, LoRa is a small trainable submodule inserted into the pre-trained models. They are used to modify the hidden representation during fine-tuning. The full name of LoRa is Low-Rank Adaptation of Large Language Models, but just forget its name for now and let's see how it works. LoRa is a module that's inserted in parallel to the modules in the pre-trained transformer model. To be specific, LoRa is inserted in parallel to the feed-forward layers in the transformer layer. While I only plot the LoRa module in this feed-forward layer, there is actually another feed-forward layer in the multi-head attention, and LoRa can also be inserted next to the feed-forward layer in the multi-head attention layer. Let's see what LoRa is doing. I just say that LoRa module is inserted next to the feed-forward layer of the pre-trained transformer models. The feed-forward layer has two projection layers and a nonlinear layer in between them. What the linear layer does is just project the input vector into an output vector with a different dimensionality using an affine transformation. The LoRa layers are inserted next to each of the two feed-forward layers. We will use the feed-forward up projection layer and the LoRa next to it, for example on the next page. The original parameters of the feed-forward layer is the pink block shown here. It takes the output from the previous layer with dimension D model and projects it into FFW, which is short for feed-forward. The LoRa module is plotted in yellow, and as the shape indicates, it consists of two feed-forward layers. The first feed-forward layer takes the same input as the pink feed-forward layer, and it projects it into an R-dimensional vector. The R is chosen to be far less than the D model. Next, the second feed-forward layer projects the vector into another vector. The resulting vector is DFFW dimension. Last, the two vectors are summed together. Recall that at the beginning of this part, I say that fine-tuning can be seen as changing the hidden representation calculated by the original transformer model. From this viewpoint, the hidden representation calculated by the pink transformer pre-trained feed-forward layer is the original H, and the vector calculated by LoRa is the incremental delta H that is used to modify the original H. Summing these two vectors give us H prime, the modified hidden representation. After introducing what LoRa is doing, we take a look at its name, which is the abbreviation of low-rank adaptation. LoRa is motivated by the observation that pre-training will decrease the intrinsic dimension of the downstream tasks. Professor Lee talked about this in the second part of the tutorial. If we write the weight after fine-tuning as the sum of the pre-trained weight W0 and the updates to the weight delta W, then LoRa's authors hypothesize that if fine-tuning has a low intrinsic dimension, then the updates to the weights delta W should also have a low intrinsic rank. Since the delta W has a low intrinsic rank, it can be approximated by its low-rank decomposition of delta W. So LoRa uses the product of two matrices, A and B, to approximate delta W, and the dimension R, which represents the rank, is much less than the dimension of the original input and output dimension of delta W. When using LoRa for fine-tuning, we only need to insert the LoRa modules next to the feed-forward layers in the pre-trained transformer layers, and add the classifier head on top of the pre-trained model. This results in a very small number of task-specific parameters for each task, and all the downstream tasks share the same set of pre-trained model parameters. The third parameter-efficient fine-tuning method we are going to discuss is called prefix tuning. Prefix tuning uses spatial submodules to modify the hidden representation of a pre-trained language model. The spatial submodules are called prefix. So what is a prefix? We first look up the word prefix in the dictionary. It says it is a group of letters added to the beginning of a word. For example, the pre here is exactly a prefix. A prefix can be seen as something that is put in front of another something. Here in prefix tuning, we add the prefix in front of something in each transformer layer, and use this prefix to modify the hidden representation. Actually, those prefixes are prepended to the hidden representation of the self-attention layer. To make things more precise, we need a quick review of self-attention. In standard self-attention, we are given a sequence of input representation for a sequence of tokens denoted by x1 to xn, shown in blue here. Each of these representations will be projected to three different vectors called the query, key, and value by some projection layers. I use Q for query, K for key, and V for value. Next, the query vector of the first token will query the key vector of position 1 by inner product and obtain the score alpha 1, 1. And then it queries the key vector of the second position to obtain the score alpha1, 2. Continue this process. The query vector of the first token will query the key vector of all the other tokens to obtain alpha1, 3, alpha1, 4, and alpha1, 5. These alphas will be passed through a softmax layer to obtain the normalized version of alpha hat. Alpha hat sums to 1, and they are usually called the attention weights. Next, those self-attention weights are product with each value vector. The first position's value vector, product with alpha hat 1, 1, and the second position's value vector, product with alpha hat 1, 2. And the third position vector product with alpha hat 1, 3, and so on. Last, the product results are summed together to form the output of the self-attention module of the first token. So this is what standard self-attention is doing. Now that we have reviewed standard self-attention, we are ready to talk about prefix tuning. In prefix tuning, some vectors are prepend to the sequence in the self-attention layer, as the P1, P2, and P3 shown in the dark blue here. These vectors P will also be projected to their corresponding key and value vectors. These prepended vectors and their key and value vectors are called the prefix. An important thing to note is the projection for the prefix is not the same as the projection of the original self-attention layer. They are newly initialized. So when we want to calculate the attention layer output for the first token, x1, we not only need to query other tokens x of the other positions, as what we do in the standard self-attention, we also need to query the prefix. That is, we use the query vector of token 1 to query the key vector of the first prefix to obtain alpha1 p1, and use q1 to query qp2 to obtain alpha1 p2. And so on. The alpha for the prefix and the alpha for the other tokens in the sequence will pass through a softmax layer to get a normalization version of alpha hat. Next, as what we do in the standard self-attention, those alpha hats will be product with the corresponding value vector. The part on the right-hand side is the same as the standard self-attention on the previous page. As for the left-hand side, alpha hat 1, P1 will be product with the value vector of the first prefix, and the second prefix value vector is product with alpha hat 1, P2, and so on. Next, all the products are summed together to form the final output for the first token. That's all for prefix tuning. As we said in the beginning of this part, prefix tuning uses prefix to modify the hidden representations that is extracted by the original pre-trained language models. Why is this the case? We can see that the alpha hat value product sum on the left-hand side is calculated using the parameters of the pre-trained transformer. So it is H, the original hidden representation calculated by the pre-trained language model. On the left-hand side, the weighted sum of the value vectors is calculated using the prefix, and the resulting weighted sum can be viewed as the delta H, which is the incremental change to the original hidden representation. Summing up the original hidden representation and the change to the hidden representation, we have the modified hidden representation, H prime. When using prefix tuning, we prepend some prefix in each transformer layer and only update those prefix during fine-tuning. The whole transformer pre-trained models are fixed and not updated. Next, we introduce another kind of parameter-efficient fine-tuning method called soft prompt tuning. Soft prompt tuning can be considered as an easier version of prefix tuning. What it does is just prepending some vectors at the beginning of a sequence at the input layer. Given an input sentence, each token in the sequence will be converted to its word embedding by the embedding layer. And then we prepend the prefix embeddings at the beginning of the sequence of token embeddings. Next, this sequence of embeddings will be processed by the pre-trained transformer models, just like what a transformer model does to a normal sequence. During fine-tuning, only those prefix embeddings are fine-tuned, while the whole transformer model is frozen and not updated. The reason this method is called soft prompt is that sometimes when we want a language model to perform a task, we will use natural language sentences or words to instruct the model what the task is. For example, if we want the model to translate a sentence, we might append the words "translate the sentence" before the input sentence. The words appended here are the hard prompts. The adjective hard means the prompts are words or tokens. We say soft prompt to be soft because the prompts are vectors instead of words in the original vocabulary. Up to now, I have introduced 4 different methods for parameter-efficient fine-tuning. Now, I will give a summary of these methods and compare their performance. We say that fine-tuning is the process of changing the hidden representation extracted by the pre-trained model. And to achieve this, parameter-efficient fine-tuning methods insert small trainable submodules into a pre-trained model and only fine-tune those submodules. Adapters are inserted into the transformer layer in a sequential way, and each adapter consists of a skip connection and 2 feed-forward layers with a nonlinear activation in between. LoRa is inserted in parallel to the feed-forward layer in the transformer layers, and the LoRa module consists of 2 feed-forward layers without any nonlinear activation. In prefix tuning, prefixes are inserted in the attention layer, and those prefixes will be queried by other tokens in the sequence. Note that those prefixes do not have corresponding query vectors because they do not query other tokens. They are the ones queried by other tokens. In soft prompt tuning, we only need to insert prefix embeddings before the first transformer layer and train those prefix embeddings during fine-tuning. We've got a question about how to determine the length of the soft prompt embedding and how to initialize the soft prompt embedding. So I show a figure here to illustrate how do we select the prompt embedding length. So the figure here shows different prompt embedding lengths and the performance on downstream tasks when the model size is different. The x-axis here is the size of the pre-trained T5 model. So when the model is small, then using only one soft prompt, which is the blue line here, will result in very bad superglue performance. However, increasing the number of soft prompts can improve the performance. However, when we increase the number of prompts to a certain extent, then the performance increase will saturate. For example, using 20 soft prompt embeddings and using 150 soft prompt embeddings will result in quite similar performance. However, when the pre-trained language model size is large enough, then even using one soft prompt embedding can result in good downstream performance. Empirically, we often choose a soft prompt embedding to be 100. The next question we want to answer is how to initialize the soft prompt embedding. And there are 3 different initialization methods proposed in the original work. The first one is random initialization. So it's just random initializing the soft prompt embedding using a uniform distribution. And the second method is to sample the most 5,000 frequent words. Sample from the most frequent 5,000 words in the vocabulary and use their word embeddings to initialize the soft prompt embeddings. The third method is using the class label in the downstream task to initialize the soft prompt embedding. And if the soft prompt embedding length is too long and the class labels are not enough, we will just fall back to sample from the word embedding using the top 5,000 frequent words in the vocabulary. The figure on the right-hand side shows different performance using different initialization. And in most cases, using random initialization will result in the worst performance. However, this seems to be mitigated when the pre-trained language model is large enough. And using class label or sample from vocabulary often results in the best performance, and they have comparable performance. So let's answer the question how to initialize the subprime embedding and how to select the subprime embedding length. The following table summarizes the 4 different methods. The second row summarizes the number of task-specific parameters using the big theta notation. The adapter and LoRa modules are very similar, and the number of task-specific parameters is proportional to D model times the down projection dimension, R. For prefix tuning, the number of task-specific parameters is proportional to the dimension of the prefix, which is D model and the prefix length. Since adapters, LoRa's, and prefix are inserted into each transformer layer, the number of parameters is also proportional to the number of transformer layers, L. Last, since subprime only prepend prefix embeddings at the first layer, the number of task-specific parameters is just D model times the prefix length, N. The third row shows the percentage of trainable parameters for each downstream task, compared with fine-tuning the whole model. As one can see, using parameter-efficient fine-tuning, the number of trainable parameters is less than 5% of fine-tuning the whole model. While adapter and LoRa have the same number of task-specific parameters in big theta notation, the R of LoRa can be chosen much less than the R of the adapters, making the percentage of trainable parameters less in practical usage. Subprime tuning requires the least parameters since it only prepends prefix at the first layer. However, the pretrained model of subprime tuning need to be large enough for it to perform well enough. Using fewer parameters during fine-tuning has benefits other than parameter efficiency. When using fewer parameters, the model trained on an in-domain dataset can have better out-of-domain generalization. The table here shows that when trained on squad, which is a question-answering dataset, the performance on the squad testing set is almost the same for standard fine-tuning and subprime tuning. But when tested on different question-answering dataset, the model fine-tuned using subprime tuning can achieve much better or comparable performance. This shows that subprime tuning can have better performance on auto-distribution generalization. Another benefit of using parameter-efficient fine-tuning is that they tend to perform well when training dataset is small. The following table shows the performance on high-resource datasets and low-resource datasets of full model fine-tuning and using adapter. The number in the parentheses is the size of the training dataset. One can see that on the high-resource datasets on the right-hand side, the adapter's performance closely follows the performance of full model fine-tuning. On the low-resource datasets on the left-hand side, the adapters consistently perform better than full model fine-tuning. So clearly, adapters' performance are comparable on high-resource data and better on low-resource data. Now that we have introduced many different parameter-efficient fine-tuning methods, a natural question is how they perform on different tasks and which one should we use. The table here shows the performance of different parameter-efficient fine-tuning methods, adapter, prefix tuning, and LoRa, and the standard full model fine-tuning on the glue benchmark dataset. First, we can see that the performance of parameter-efficient fine-tuning closely follows the performance of full model fine-tuning, and sometimes an adapter can surpass the performance of full model fine-tuning. However, there is no parameter-efficient fine-tuning method that consistently performs the best on all the datasets, so one may need to test all the different kinds of parameter-efficient models to find the best one. Still, those parameter-efficient fine-tuning methods all have comparable performance compared with standard fine-tuning. In summary, parameter-efficient fine-tuning is a very useful technique for fine-tuning pre-trained language models that gives good performance and requires less task-specific parameters for each task. In the last part of the tutorial, we are going to discuss how to use pre-trained language models from another aspect. In this part, I will introduce how these pre-trained language models can be used with different amounts of data. I will first give a brief idea of what the amount of data is referring to here, using the following few slides. Given a pre-trained language model and a downstream task, our goal is to obtain a model for the task. In standard fine-tuning, we assume that we have sufficient label data for the task. In some cases, not only do we have the label data for the target task, but we might also have the label data for other tasks. So it is important to know if using the dataset from other tasks can help us fine-tune the model on the target task. In some cases, the label data of the target task may be scarce, and it might be very difficult to use standard fine-tuning to achieve good performance. However, sometimes we have the unlabeled data for the target task, and we can use the unlabeled data to improve the performance of the downstream task. In a quite extreme but practical scenario, we might not even have any training data for the target task, so it is impossible to fine-tune a model. In short, we may have different amounts of labeled or unlabeled datasets for the target task and other datasets for other tasks. How should we use different combinations of the datasets to perform well on the target task? This is the question we are going to answer in this part of the tutorial. So first, let's start with a special type of fine-tuning called intermediate task fine-tuning. Intermediate task fine-tuning uses the label dataset of other tasks to improve the performance of the target task. Assume that we have the target task dataset. So in standard supervised fine-tuning, we just fine-tune the pre-trained language model using standard fine-tuning or the parameter-efficient fine-tuning method introduced in the previous part. However, in intermediate task fine-tuning, we further assume that we have the label dataset for other tasks. What intermediate task fine-tuning does is very straightforward. First, fine-tune the model for the intermediate task, as what we do usually. These tasks are called the intermediate task fine-tuning. Next, we use the model trained on the intermediate task to initialize the model for the target task and train the model on the target task. The logic of this method is very easy. The knowledge related to the intermediate task may be beneficial to the target task. So we can transfer the knowledge in the intermediate task by first fine-tuning the pre-trained model on the intermediate tasks. However, intermediate task fine-tuning is not guaranteed to have better performance of the target task. So it is necessary to know what kind of intermediate task is the most beneficial for the target task. In the paper shown here, the authors explore the transferability among 33 different natural language processing tasks. These tasks can be categorized into 3 types: sequence classification, question answering, and sequence labeling. Next, they use each task as an intermediate task and use other tasks as the target task. This results in a total of 33 by 33 combinations. We show the result of classification tasks here in this table. The row corresponds to different target tasks, and the columns corresponds to different intermediate tasks. The diagonal elements are the performance not using the intermediate task fine-tuning, denoted by PT. The off-diagonal terms are the performance of intermediate task fine-tuning. For example, the element is the performance of using SNLI as the intermediate task and further fine-tuning on the target MRPC dataset. The performance of intermediate task transfer from task S to task T is denoted as PS2T. The numbers in blue indicate that there is a positive transfer, meaning that PS2T is higher than PT. It can be easily seen that intermediate task fine-tuning can bring positive transfer in most cases. For a target task, the number in boldface is the best performance among all other intermediate tasks. For example, among all the other task classification tasks, the best intermediate tasks for WNLI is COLA. Next, we compare the intermediate task fine-tuning transferability of different types of tasks. The table here shows the average best relative transfer gain between different types of tasks. The relative transfer gain is defined as the ratio between the difference between PS2T and PT over PT. Each entry of the table is the average best transfer result of different target tasks. For example, the first entry is the average best transfer results when the target tasks and the intermediate tasks are classification tasks. The number in the parentheses indicates how many target tasks have positive relative transfer gain. From the table, we can see that the best transfer gain is obtained when using the same type of tasks as the intermediate task, and all the tasks can benefit from the intermediate task transfer. In the previous page, both the intermediate task and the target task are assumed to be very sufficient. We turn to a case when the intermediate task or the target dataset is limited to 1000 training samples. When the target task training examples are limited, the transfer result is more observable than using the full dataset. And even when the intermediate task has limited training samples, the intermediate task fine-tuning is still useful. This indicates that intermediate task fine-tuning is beneficial in different amounts of data. Although intermediate task fine-tuning is useful, we usually don't know what is the best intermediate task to use, and we will end up fine-tuning a model with all possible intermediate tasks and select the best one. When using standard fine-tuning, this would require a lot of space to store those models. For example, fine-tuning the largest T5 model on an intermediate task results in a downstream model with 13 billion parameters, and fine-tuning on 4 different intermediate tasks results in 4 models of the same size. This is very space-consuming, and this is exactly why we have parameter-efficient fine-tuning. By using subprompt tuning, the number of parameters of each intermediate task reduces to about 200,000. After training the subprompts on the intermediate task, the subprompts are used to initialize the subprompts of the target task. This is called the subprompt transfer. This figure shows the relative transfer gain of the subprompt transfer. Each block is a relative transfer gain of transferring the subprompt trained on the intermediate task to the target task. We can see that subprompt transfer does not always result in a positive transfer. However, MNLI is a good choice as the intermediate task, since it results in positive transfer gain on all of the 10 target tasks shown here. But if the transfer is not always positive, how do we choose the best intermediate task? More precisely, when we are given a prompt embedding library with the subprompts of different intermediate tasks, how can we find the best intermediate task and the most beneficial subprompt embedding to use? The key idea is to view each of the subprompt embedding in the prompt embedding library as the task embedding that represents the task. So, when given a target task, we directly use subprompt tuning to fine-tune on the target task. In this step, the subprompt embedding is not initialized using the subprompts of the potential intermediate tasks in the prompt embedding library. After obtaining the prompt for the target task, we can use these prompts as the task embedding and query the prompt embedding library to find the most similar prompt embedding. After finding the intermediate task whose task embedding is the most similar to the target task's prompt embedding, we use the subprompt of the intermediate task to initialize the subprompt embedding of the target task, and use subprompt tuning to fine-tune the model. The subprompt transfer of using the task embedding cosine similarity to find the best intermediate task is shown in the table. The first row shows the performance of direct subprompt tuning without using subprompt transferring. The performance is averaged over 16 different target tasks. The second row is the result of brute force search over 48 possible intermediate tasks, and select the best result for each of the 16 different target tasks. The number here is the absolute transfer gain and the relative transfer gain, and the small number is the standard deviation. Next, the lowest block is the performance of using cosine similarity to find the intermediate task to transfer from. The top k here means that we select the top k similar intermediate tasks based on cosine similarity, use the k different intermediate tasks to perform subprompt transfer, and then select the best model among the k different models. It is expected that increasing the number of k can improve the subprompt transfer performance, since the more intermediate tasks we choose, the more possible that the best task can be chosen. But the subprompt transfer is still useful even when we select the intermediate task whose prompt embedding cosine similarity is highest with the target task, which is the case when k is 1. So this again verifies the usefulness of intermediate task fine-tuning. There is a question about how to use multitask fine-tuning to improve the target task's performance. So multitask fine-tuning is a bit different from the intermediate task fine-tuning we have talked about, but the core concept is the same. It's just using the label data from other tasks to improve the performance of the target task. So in multitask learning, we have the auxiliary dataset, and this is just the dataset that are another target task, and we have the target task dataset. So in multitask fine-tuning, we just combine two datasets and use those datasets to fine-tune a pre-trained language model. So the fine-tuned language model is fine-tuned on the auxiliary task datasets and on the target dataset at the same time. So the core concept is that we hope learning from the auxiliary dataset can help learning the target dataset. However, there is a problem in this multitask fine-tuning. It's just we don't know how to select the auxiliary datasets. And this can be formulated to another problem, that we want to know how to weight the loss of different tasks. So if the task is very important to the target task, then this auxiliary task should have larger weight of the loss. And if the task is not very important, then the weight of this task can be smaller. And how to determine the weight is not a very easy problem. And I list a paper here that addresses this problem. So if you are interested in this topic, you can refer to this paper. In the previous part, we introduced intermediate text fine-tuning, which use additional label data for other datasets. Next, we consider a different scenario when we only have the label data of the target task. Moreover, we are going to consider the case when the label data is limited. In standard fine-tuning, we usually have a large amount of label training data. For example, each of the datasets in the GLUE benchmark consists of thousands of label training samples. What we are doing to the model during fine-tuning is providing the model with samples and hoping the models to find the pattern from the dataset. Take the natural language inference task as an example. In this task, the model is given a pair of sentences. The first sentence is called the premise, and the second sentence is called the hypothesis. There are three different possible relationships between the premise and the hypothesis: entailment, meaning that the second sentence can be inferred from the first sentence. Contradiction, meaning that the second sentence contradicts the first sentence. And neutral, which means that neither entailment nor contradiction. In standard fine-tuning, what we are doing is giving the model a bunch of sentence pairs connected with spatial tokens SEP. And each sentence pair has a corresponding label that represents the class. The model needs to understand what the task is doing and understand what each label means based on the training samples. This is, of course, possible when the training data are a lot. However, in reality, training data is seldom a lot, so it is more realistic that we only have very few label training samples. This is called few-shot learning, and the number of training samples we are talking about here is normally less than 100. So consider that you are given only 2 examples formatted as how we format them in standard fine-tuning. And suddenly you are given a 3rd example and asked you to provide an answer. You will probably have no idea what this is doing. You cannot know what the 2 sentences here mean, and you don't understand what the numbers correspond to. So clearly, it is very hard to understand the task when only a few samples are given, even for humans, so not to mention for the pre-trained language models. However, if I reformat the questions into the ones shown on this page, by connecting the 2 sentences with the phrase, "Is it true that?" and change the labels from numbers into yes or no, then humans should be able to perform the task, since we can better understand what this task is about. This is the key idea of prompt tuning. We can format the downstream tasks into human language questions and prompt the models to answer the questions using human language. The natural language prompts should be easier for the model to understand because during pre-training, the model has already understood human language to a certain extent, so the model can better use this ability used in pre-training. Moreover, in prompt tuning, the downstream task will be formatted just like the pre-training task, so the model can better use the knowledge learned during pre-training. I will explain this part in a more detailed way later. But first, let's take a look at the word prompt. The word prompt means to induce something to action, or to inspire, based on the dictionary. So when using prompt tuning, we are using natural language to inspire or to induce the model to perform the downstream tasks. Formally, in prompt tuning, given a sample in the dataset, we use the prompt template to convert the sample into a human language prompt. The prompt consists of a mask token. Next, we feed the natural language into the pre-trained mask language model and ask the model to fill in the mask position. Next, when obtaining the mask language model prediction of the mask position, we will need to convert the language model prediction, which is the words in the vocabulary, to the labels of the downstream tasks. This is done by something called a verbalizer. I will explain each part in a more detailed way. The first ingredient in prompt tuning is the prompt template. The prompt template converts the data point in the dataset into a natural language prompt. The prompt template defines how to combine the features in the dataset into a natural language sentence, and the prompt template will have a mask token for the pre-trained language model to fill in. Different tasks will have different templates, and they are mostly handcrafted. We take natural language inference as an example here. The natural language prompt template here says that given a data point, we just simply connect the premise and the hypothesis with a question mark, a mask token, and a comma. So the data point on the left-hand side is converted into the natural language prompt on the right-hand side. The second ingredient in prompt tuning is the pre-trained language model. The pre-trained language model is used to predict the missing word in the natural language prompt. This is exactly what the language model has been learning during pre-training. The natural language prompts makes the downstream tasks look just like the pre-training task. This reduces the gap between pre-training and downstream fine-tuning, and more easier for the pre-trained model to transfer the knowledge from the pre-trained model. The last ingredient in prompt tuning is called verbalizer. The verbalizer defines what word in the masked language model prediction correspond to a specific class of the downstream task. We need verbalizer because the masked prediction is a probability distribution over the whole vocabulary, but our goal is to obtain the downstream task prediction. So we need to define what word in the vocabulary correspond to what class in the downstream task. In this natural language inference, we manually define that the word yes corresponds to entailment, the word maybe corresponds to the class neutral, and the word no means contradiction. Then, given the language model and the masked prediction, we select the prediction score of the words that correspond to the labels and then normalize them to get the prediction over the class prediction of the downstream task. With the prompt template, the pre-trained language model, and the verbalizer, one can fine-tune on the downstream task. I'm going to summarize the whole idea of prompt tuning using the following slide and the example in this slide, which is a data point drawn from an NLI dataset with the premise Mary likes pie and the hypothesis Mary hates pie. So given this data point and the predefined prompt template shown on the right-hand side, the data point is converted into the following natural language sentence: Mary likes pie, question mark, mask token, comma, Mary hates pie. And this sentence is fed into the BERT model. And during fine-tuning, the BERT model should learn that since the premise and hypothesis in this example contradict each other, so the mask token should be filled in with the word no. So the complete sentence is like Mary likes pie, question mark, no, comma, Mary hates pie. For other examples, if the two sentences entail each other, then the mask token should be filled in with the word yes. And if the two sentences are neither contradiction nor entailment, then the mask token should be filled in with the word maybe. So using the pre-trained language model, we can obtain a probability distribution over the whole vocabulary space for the mask token. But what we want is the probability distribution over the label space. So this is what the verbalizer does. The verbalizer tells us that we just need to select the probability of yes, no, and maybe, and normalize it into a probability distribution. Then this probability distribution corresponds to the probability distribution of entailment, contradiction, and neutral. So we have the probability distribution over the label space as we want. So this is the whole idea of prompt tuning. In prompt tuning, the whole pre-trained language model is fine-tuned. Keep in mind that the prompt tuning I'm talking about here is not the soft prompt tuning I introduced in parameter efficient fine-tuning. In soft prompt tuning, we insert trainable prompt embeddings at the input layer and only update the prompt embedding during fine-tuning. In prompt tuning I'm talking about here, the prompt templates are fixed, and the whole pre-trained language model is fine-tuned during fine-tuning. Here is a comparison between prompt tuning and standard fine-tuning. There are mainly two differences. The first one is the input format. The input for prompt tuning is a natural language prompt with a mask token to fill in. The input format for standard fine-tuning is simply combining sentences with a separator token. The second difference is that standard fine-tuning utilizes a newly initialized classifier head for the fine-tuning, while prompt tuning simply uses the language model head and the verbalizer to predict the class of the downstream task. These differences also make the performance of prompt tuning and standard fine-tuning to be very different when the training data are not a lot. From the following figure, one can see that when the training data is a lot, the performance of prompt tuning and standard fine-tuning is almost the same. However, when the label data is scarce, prompt tuning gives performance far better than standard fine-tuning. So prompt tuning is very useful in few-shot learning. This is mainly because prompt tuning incorporates human knowledge through the prompt template, and it introduces new parameters during fine-tuning. In the following part, I want to talk about verbalizers more, which is an important component of prompt tuning. Previously, I said that the verbalizers are manually designed. Manually designing the verbalizer often requires task-specific knowledge, and we have to know what might be the best vocabulary for a specific class. I'm going to introduce a special kind of verbalizer that requires no task-specific knowledge. This is called the prototypical verbalizer. The key concept of the prototypical verbalizer is that instead of using an existing word in the vocabulary to represent a class in the downstream task, we can directly learn another spatial prototype vector to represent each class. During prompt tuning, the pre-trained model is fine-tuned to make the hidden representation of the mask token to be more similar to the prototype vector of the corresponding class. The figure here uses news title classification as an example. Given a news title, the goal is to categorize the news into 3 different classes: world news, tech news, and sports news. During training, we first initialize a learnable prototype vector for each class to represent that class, which is the star sign in the figure. Next, we convert each training sample into a natural language prompt using the prompt template, and extract the hidden representation of the mask token calculated by the transformer models, and pass it through a linear layer to get the instant representation of the input. The linear transformation layer here is newly initialized in the downstream task. The instant representations are the circles in the figure. The model and the prototype vectors are fine-tuned using contrastive learning, which has 2 components. The first one is the instance-to-instance contrastive learning. For an instance representation, we use the other instance representations of the same class as the positive samples, and the instance representation of different classes as the negative samples. This will teach the model to distinguish the instance representations of different classes. Another component of contrastive learning is the instance-to-prototype contrastive. In this contrastive, the positive sample of an instance is the prototype vector of the same class, and the negative samples are the prototype vectors of the other classes. This will make the instance representation and the corresponding prototype vector to be more similar. After the model is fine-tuned using contrastive learning, it can be used for inference. During inference, given an input news title, we convert it into the natural language using the same template, and then extract the instance representation using the fine-tuned model. Next, we compare the cosine similarity of the instant representation with the prototype vectors of different classes. We choose the most similar prototype vector as the prediction. One can see that when using a prototypical verbalizer, we do not predict what word in the vocabulary should be filled in the mask. This is because the prototypical verbalizer does not need to assign a word in the vocabulary for each class in the downstream task, because we are not using a word in the vocabulary to represent a class. We are relieved of using task-specific knowledge of selecting the verbalizer. The following table compares the performance of different verbalizers on 4 different datasets in the few-shot scenario. The K here represents the number of training data for each class. There are 3 different verbalizers shown here: the manual verbalizer selected by humans, and the proto-verb I just introduced. The search verb is another kind of verbalizer that searches the verbalizer from the vocabulary. This also requires no task-specific knowledge. But I didn't introduce this one because the performance is always worse than the prototypical verbalizer. First, we can see that the performance of the manual verbalizer is always quite good for different k. A notable point is that even when there is no training data and the model is not fine-tuned, which is the case when k equals to 0, the manual verbalizer can still achieve decent performance on most datasets. Next, we see that the performance of the prototypical verb is much better than the search-based verbalizer under all different scenarios. Proto-verb also gives quite a good performance when the training data for each class is only 1. This shows that proto-verb is very powerful while requiring no task-specific knowledge. Last, the performance of proto-verb is often comparable to or better than manual verbalizer when there are more training data. The main takeaway here is that a manual verbalizer is mostly the best no matter how much training data you have. However, the prototypical verbalizer is a nice choice if it is hard to select a word for each class. In the last part of prompt tuning for fuchsia learning, I will introduce a simple method to boost the performance of prompt tuning called LMBFF. LMBFF aims to give better fuchsia performance using a pre-trained language model. In standard prompt tuning, we just convert the sample into a natural language prompt that contains a mask token and use the mask language model to predict the missing word and use the verbalizer to get the class prediction. LMBFF appends demonstrations to the original prompt template. It converts the training sample into the corresponding natural language prompt and fills in the mask token with the corresponding label word. The figure here is an example of a sentiment classification task that classifies the sentiment of a movie review into positive or negative. The demonstration contains a positive movie review and the phrase, "It was great," and a negative movie review and the phrase, "It was terrible." During training and testing, all the inputs have prompts and demonstrations. In this way, the model will have a better idea what the task is doing by observing the demonstration, and it will know that if the movie review is positive, it should fill in the mask with the word "great," and if the movie review is negative, it should fill in the mask with the word "terrible." The following table shows the performance of LMBFF on 8 different tasks, when the total training samples for each task is only 16. The number in the parentheses is the standard deviation due to different training set split. One can see that prompt-based fine-tuning can obtain far better results compared to standard fine-tuning. Using demonstration can further improve the performance. The number in the parentheses is the standard deviation, so one can see that using demonstrations can lower the variance of the performance due to different training dataset split. Here we've got a question from our audience that asks, what's the difference between prompting and probing? So I'm going to use about 2 slides to explain the difference between them. And so first, let us start with introducing how the word prompt emerged in the recent NLP community. So in fact, the concept of prompting is first used in recent NLP community for probing the factual knowledge of a pre-trained language model. So for example, when we want to know if the language model knows what subclass English Bulldog belongs to, then we will format this factual knowledge question into a natural language prompt. English Bulldog is a subclass of blank, and we will use the mask language model to fill in the blank. And if the language model can successfully fill in the blank with the word dog, then we say that the language model have the factual knowledge about English Bulldog is the subclass of dog. So after this kind of factual prompting or factual probing, researchers have started to think that if we can use prompt to probe the factual knowledge of a language model, why don't we just use prompt to fine-tune the language models? So Now, probing is the process of exploring what knowledge is encoded in the pre-trained language model. And this knowledge includes the linguistic knowledge Professor Lee has introduced in part 2, and the factual knowledge I just mentioned. And in the process of probing, the pre-trained language models are often fixed. So we are just using the knowledge that is already encoded in the pre-trained language model. However, prompting means that we use a language model to query the pre-trained language model. And when we are trying to query the pre-trained language model, perhaps in a downstream task, the language model can be fine-tuned, and it can also be not fine-tuned. So the purpose of prompting and probing are different. So this is the difference between probing and prompting. Next, we move to semi-supervised learning using pre-trained language models. In semi-supervised learning, we have both the labeled dataset and the unlabeled dataset for the target task. And the labeled dataset is often not a lot. The core idea of semi-supervised learning is to first use the labeled dataset to train a decent model, and then use the model to label the unlabeled data. The labels predicted by the model are called pseudo-labels. Next, we use the unlabeled dataset and their pseudo-labels to fine-tune another model. The most important and the most difficult part here is that we need to guarantee that the quality of the pseudo-labels are good enough. So we have to train a decent model using a limited number of labeled data. I will introduce two distinct methods to do this. The first one is called pattern exploit training. The method is based on prompt tuning, and the basic idea is to use prompt tuning under labeled data scarcity and use the trained model to label the unlabeled dataset. And then the unlabeled dataset will be used to train the final model. The first step of pattern exploit training is to select different pairs of prompt templates and verbalizers. For each pair of verbalizer and prompt templates, we use prompt tunings to fine-tune the model using the target label training data. After the first step, we have different models that are trained with different templates and verbalizers. The next step is to use the trained model to predict the unlabeled dataset. For each sample in the unlabeled dataset, we use different models to predict the class distribution of the sample. Then we sum the class prediction of different models together and normalize it into a probability distribution. And we call this the sublabel because it is a probability distribution and it is not a one-hot vector. After this step, each unlabeled sample will have a corresponding sublabel that was predicted by the ensemble of all the prompt tuning models. The last step is to train a model using the unlabeled samples and sublabels to fine-tune a pre-trained language model. The performance of pattern exploit training using a different number of training samples is shown in the table. The T here means the number of labeled training samples. The supervised here means that the model is trained using standard fine-tuning only on the labeled dataset, and the PAT means using the labeled samples and the other unlabeled samples for training. One can see that PAT always performs better in all scenarios. While PAT requires additional unlabeled samples are not very hard to acquire in reality. In summary, PAT uses human-designed verbalizers and prompt templates to overcome the labeled data scarcity problem, and uses the model trained by prompt tuning to label the unlabeled data. The next semi-supervised learning I'm going to introduce is called self-training with task augmentation, abbreviated as STRATA. Similar to pattern exploit training, this method also trains the model on the labeled data to label the unlabeled dataset and obtain the pseudo-label. The model used for labeling the unlabeled dataset is called the teacher model. Next, the labeled data and the pseudo-labeled data are combined to train another model called the student model. This process is called self-training. And again, the quality of the pseudo-label is critical to the final performance. So how the teacher model is trained is very important. Different from PET, which uses prompt tuning to solve the issue of labeled data scarcity, Strata resorts to intermediate task fine-tuning. In Strata, the intermediate task fine-tuning is called task augmentation, and it is basically intermediate task fine-tuning. The core idea is to first fine-tune the prediction model on the intermediate task that is related to the target task, and then use the model fine-tuned on the intermediate task to initialize the model for the teacher and student model. However, we only have the unlabeled data for the target task. How could we create the intermediate task fine-tuning dataset? In Strata, they generate a natural language inference dataset using the unlabeled dataset, and use the synthetic natural language inference dataset as the intermediate task. We decompose the task augmentation part into 3 steps. The first step is to train a generator model that can generate the NLI dataset. In Strata, they assume that there is an additional labeled NLI dataset to train the initialized dataset generator. This is not very unrealistic since labeled NLI datasets are easy to obtain. They use this NLI dataset to train a dataset generator by fine-tuning the T5 model. Given a label and a premise, the generator is trained to generate a hypothesis, such that the relation between the given premise and the generated hypothesis corresponds to the given label. For example, if a data point in the NLI dataset has the label entailment, then we give the model the word entailment and the premise, and the model learns to generate the hypothesis that entails the premise. After the data generator is trained, we use the unlabeled dataset of the target task to generate the synthetic dataset for the natural language inference in step 2. Assume that our target task is a sentiment classification task, and the unlabeled data is a bunch of movie reviews without ground truth. Then for each movie review, we randomly select a relation in the NLI task, and combine it with the unlabeled movie reviews, and feed it into the NLI data generator model. For the example in this figure, we expect that the generated hypothesis to entail the unlabeled movie review. After this step, we will have a synthetic NLI dataset, and the premises in this dataset are exactly the unlabeled data of our target task. In the last step, we use the synthetic NLI dataset as the intermediate task to fine-tune the pre-trained language model. After the model is fine-tuned, the model is used to initialize the teacher model and the student model in self-training. Transferring from this synthetic intermediate task is beneficial because the intermediate task is in-domain to the target task. For example, if the target task is a movie review sentiment classification task, then the intermediate task is a movie review natural language inference task. In this way, the model fine-tuned on the intermediate task will capture a sufficient amount of knowledge of the target task, so it can perform well on the target task, even if the labeled data are scarce. In this figure, we show the performance of Strata on 2 different classification tasks, SST2 and SciTel. The red line is the performance of BERT using the whole training set, and the blue line is the performance of fine-tuning BERT using limited training data. The green line is the performance of Strata. We can see that the performance of Strata is far better than standard fine-tuning when the label data are limited. Strata's performance also closely follows the performance of supervised learning with the full training dataset. As a short summary, when the unlabeled data are available, using those unlabeled data wisely can significantly improve the performance of the target dataset. In the last part, we are going to talk about a very extreme but realistic scenario: zero-shot learning. In zero-shot learning, we don't have any training data for the task. In this case, we need a model that can perform well on an unseen task without seeing any label data. The problem now becomes, how do we make a model to be able to perform zero-shot inference? You might hear of the powerful GPT-3, which can perform zero-shot inference when the task description is given. For example, just tell GPT-3 to translate English into French, and give it the word cheese. Quite surprisingly, GPT-3 can generate cheese in French. Researchers have investigated why GPT-3 can perform zero-shot learning, and they propose a hypothesis. The hypothesis is that during the pre-training of GPT-3, the pre-training data is just like a mixture of different tasks, and the multi-task pre-training enables the model to perform zero-shot inference. For example, there are a lot of FAQs on the web, and the GPT-3 is trained on corpus drawn from the web. So pre-training on this corpora is like learning a question answering task. As another example, we can often find short summaries of an article on the internet, and pre-training on this is like learning a summarization task. So to test this hypothesis, researchers fine-tune a T5 model by multitask learning. They use a mixture of tasks for intermediate task fine-tuning, and test the zero-shot ability of the fine-tuned model. These tasks are formatted into human language prompts, just like what we do in prompt tuning. For example, the summarization task is converted into a paragraph appended by the question, how would you rephrase that in a few words? The T5 model is fine-tuned to generate the summary. For the QA dataset, we feed in the model, I know the answer to the question is in the paragraph. Can you tell me what the answer is? And the T5 is fine-tuned to generate the answer. After multitask fine-tuning, we test the fine-tuned model's performance on unseen tasks. The fine-tuned model is called T0. In their experiment setting, the intermediate tasks used for fine-tuning are of course different from the tasks for testing zero-shot inference. Moreover, they further require that the task's type used for fine-tuning should be different from the task type used in zero-shot inference. For example, if during intermediate task fine-tuning, T5 is trained using a sentiment classification dataset, such as SST2, then we cannot use a different sentiment review classification dataset, such as IMDb, to test the zero-shot inference performance. To do this, let's categorize NLP datasets into different types, and using some types of the tasks for fine-tuning, which are the tasks in orange, and use the other types of the task, the ones in green, for zero-shot inference, including natural language inference. The performance of the T0 is the green dots in the figure, and different dots represent different prompt templates used in zero-shot inference. One can also see that the variance due to different prompt templates is quite large, meaning that how to select the prompt is critical to the zero-shot performance. The dots in red are the performance of GPT-3 of different sizes, and the blue ones is the performance of T5 without multitask intermediate task fine-tuning. You can easily see that the green dots are always better than the blue ones on average. This shows that multitask fine-tuning can indeed enable a model to perform zero-shot inference on unseen task. By now, we have completely gone through how to use pre-trained language models when we have different amounts of data. I'll give a very short summary in 2 slides. First, pre-trained language models can be used when we have different amounts of label training data. Unlabeled training data are also very helpful if they are used correctly with some spatial design. Additionally, labeled datasets of other tasks may also be helpful to transfer some useful knowledge. Next, Incorporating human knowledge is often useful, especially when label data is insufficient. For example, handcrafted prompt templates and expert-selected verbalizers can significantly boost performance. So if there is no further questions, I think we can first move on to the conclusion and future work part, and then close this tutorial with the Q&A session. So I'm going to give a brief summary of what we have discussed today, and the first part is a simple introduction, and the second part we have talked about. There are a lot of researchers that try to study why precision language models are useful, and they have research in different aspects, from linguistic aspects to some interesting domain transferability findings. However, there is still not very sufficient research on why precision language models work so well in a theoretical fashion. There is no theory that tells us why using precision language models can improve the downstream performance. And while there are a lot of theoretical works on contrastive learning and self-supervised learning in computer vision, there are those works cannot be directly used in precision language models. So there is still a large gap between the empirical success of precision language models and their theoretical backgrounds. So this is an open question for this part. And the third part of our tutorial discusses contrastive learning and using precision language models. And we show that contrastive learning is a very strong method for learning sentence embeddings. And these sentence embeddings can be used in a lot of different NLP tasks. For example, sentence classifications, retrieval, and a lot other tasks. And we have also discussed how to reduce the task-specific parameters when fine-tuning the precision language model, and how to use these models in the downstream tasks when we have different amounts of data, label and unlabeled data, and the model for target task, the data set for target task, and the data set not for the target task. And some contents we discuss are simplified for the ease of explanation. And if listeners are interested in those details, then we have cite those papers in each slide, so you can refer to those papers if you are interested in them. And while we have discussed a lot of findings and success in precision language models and how to use them and why do they work, there is actually a long way to go. For example, while we try to answer why precision language models are useful, as Professor Lee has said in the second part, we actually don't know why exactly they are useful. We just find some interesting findings that partially explain what precision language models have learned during pre-training. But whether those things learned during pre-training are critical to the downstream performance is not really understood so well. So those observations and the conclusion that precision language models work well on the downstream task are only association observations. They are not causal statements that tells us because the language model learn linguistic knowledge, so the language model can perform well on the downstream task. We don't have such a statement yet. So that may be some future directions that we need to complete. And another open question is for contrastive learning is about how can we create better positive and negative samples in contrastive learning. And as Yong-Sung have mentioned in part 3 of our tutorial, positive samples are not very easy to create in natural language processing. As opposed to computer vision, we can just use random cropping or resizing the image. But in in natural language processing, we cannot just crop a sentence and use it as a positive sample. And there are some evidences that show that current sentence encoders that are trained with contrastive learning actually illustrate some pathological behaviors. And to be specific, those sentence encoder models are not sensitive to subtle textual label change. For example, if two sentences have high lexical overlap, but their meaning are very different, then sentence encoder tend to give the sentence pair a high similarity score. So that means the way we are creating positive and negative samples now cannot fully make the sentence embedding model to know what similar sentences should be like and what dissimilar sentence should be like. So this is also an open question. And as another future work, we can, for the parameter efficient fine-tuning part, can we combine different parameter efficient fine-tuning methods with other methods that cut down on the size of the parameter, including model pruning, model compression, or weight quantization? And this is actually an important topic, since even if we are using parameter efficient fine-tuning methods, we still have a large language model. And for example, the largest GPT-3 model is 100 or something billion parameters. So if we want to use parameter efficient fine-tuning on this large model, it is still very space consuming. So it would be great if we can cut down on the number of the task-specific parameters, and we can simultaneously cut down on the parameter size of the pre-trained language model itself. So I think this is something that is not explored yet. And there are a lot of practical future works, including how these few-shot learning methods perform on domain-specific data sets. Because these few-shot learning methods are mostly conducted on widely used natural language processing benchmarks. And it is unclear how those, for example, we have a medical question answering data set. Then we don't know how this few-shot learning will perform on such a domain, because medical domain is not something people work in natural language processing will usually encounter. So if the performance of few-shot learning on those medical question answering dataset is not good enough, how can we adapt the language model to different domains and allow them to perform downstream tasks in few-shot or zero-shot manner? And even if those performances are good enough, can we really trust those models perform the model's prediction? And how can we explain the decision of those pre-trained language models? So this is an interpretability and explainability issue. And this is very important because users would like to know how the model make the decision. And if they can know that, they might find the model prediction to be more convincing. So this is a very important topic, but and is still developing now. And a very important future work is, does the language model really understand human language? And the reason why I raise this question, because there are some recent studies that show that even if the prompt, when we use prompt tuning, or when we use or the prompts used in zero-shot inference, even if they are nonsensical, prompt tuning can still work. So this means that human knowledge may not be really so important in prompt tuning. And if this is the case, then what does the language model really understand? What is the language model really relying on when it is performing this task? And why are there some prompts that are better than other prompts? If there are some prompts that are better than other prompts, does that mean that the language model cannot fully understand other prompts? So let's all create the question that pre-trained language models may not be able to fully understand human language. And the last open question on pre-trained language model is, when deploying these pre-trained language models, the model should change over time because the world is changing over time. However, it is very resource consuming to retrain the model, so it is important to know how to adapt the language models through time and remove the outdated knowledge and insert new knowledge in the pre-trained language model. So as a summary, while pre-trained language models have made significant progress in natural language processing through the past few years, there is actually still a long way to go. And we hope this tutorial can help everyone understand where we are now and where we need to go. So that's all for today, and thank you for listening. And we are happy to take any question now. So is there any questions regarding pre-trained language models and the topics we talk, or any discussion? Okay, since it seems that no one have any questions. So again, thanks everyone, and it is really a precious experience to give a tutorial here at AACL, and I want to thank the other two tutorial instructors and thank all the audience to join us in this tutorial, and we wish you a good evening.
Bye.
Bye.